Example problem 3.20 asks us to determine the overturning stability of the reinforced cantilever retaining wall shown in figure 3.83 of the textbook. It also asks what is the sliding force that needs to be resisted at the base of the footing. Before we begin our calculations, we are told that the force being exerted by the concrete equals 150 pounds per cubic foot. The force being exerted by the soil is equal to 110 pounds per cubic foot, and the equivalent fluid density is 35 pounds per cubic foot. In solving this problem, we will first assume a 1 foot wide strip of wall represents the entire wall. We then need to calculate the force being exerted by the wall, the base, and the soil. The force being exerted by the wall is 1 foot times 10.67 feet times 1 foot times 150 pounds per cubic feet, or 1,600 pounds. The force being exerted by the base is equal to 1.33 feet times 7 feet times 1 foot times 150 pounds per cubic feet, or 1,397 pounds. Finally, the force being exerted by the soil equals 4.5 feet times 10.67 feet times 1 foot times 110 pounds per cubic feet, or 5,282 pounds. When evaluating the moments about the toe at A, we find ourselves seeing that the maximum pressure at depth H works out to 35 pounds per cubic feet times 12 feet, or 420 pounds per square feet. We then look at the horizontal fluid force, which is 1/2 times 420 pounds per square feet times 12 feet, or 2,520 pounds. That gives us a moment about the toe at A of 2,520 pounds times 4 feet, or 10,080 pounds per feet. When calculating the righting moment, or the stabilizing moment about A, we need to refer back to the W calculations we did at the beginning of the problem. That brings us 1,600 pounds times 2 feet plus 1,397 pounds times 3.5 feet plus 5,282 pounds times 4.75 feet, for a total of 33,180 pounds per foot. Now that we have our two moments, we can calculate the safety factor against overturning. We take the righting moment of 33,180 pounds per foot and divide it by the moment about the toe A, 10,080 pounds per foot, which brings us a factor of 3.29. This number is greater than 1.5, which means the retaining wall is stable against overturning about the toe. Frictional resistance developed between the bottom of the footing and the soil must be a factor of 1.5, or the standard safety factor, times the horizontal fluid force, P4, 2,520 pounds, or a total of 3,780 pounds.
All right, my name is Jonathan Tate Moore. I'm a part of group project number 7, and the problem assigned to me was 4.2. and I'm going to be working at the initial method instead of the alternative. And basically, to start this problem out, what we're looking at here is a decking structure that's held by 9 different columns, each labeled A, B, C, and 1, 2, 3. And there's also certain dimensions with them as well. You can see each planks are not the exact same length, so a bit of an addition to 4.1. And a little bit of information that we also brought from 4.1 was the deck's dead load, which was 8 pounds per square foot, and the deck's live load, which was 60 pounds per square foot. The beam self-weight, which was going to be 10 pounds per foot, and the column self-weight, which is 100 pounds. And starting off, the first thing we want to do is we want to add the 2 decks loads together to get the uniform load, which is the load uniformly spread out over this entire structure. And once we add those 2 together, we're actually just going to get 68 pounds per square foot. And then to do this, represent this in form of actual load. It's going to be W equals 68 pounds per square foot times 1 foot, which is actually the given unit from 4.1. That's going to be the tertiary area of each unit. And once you multiply those 2 together, it's going to give you 68 pounds per foot. Alright, so for the second part of this problem, we're going to be looking at the reactions for the beams. And the only 2 reactions we have are going to be A to B and B to C. And this can simply be done by using the formula R equals the total load times the length over 2. And so for A to B, all we have to do is simply plug in our total load, which we found from up here, to be 68 pounds per foot, and multiply that by 6, which is going to be the length. And we can see that from the diagram from A to B. We see it's going to be 6 feet. So go ahead and plug that 6 in over 2. That's going to give us a reaction for A to B of 204 pounds. Same thing with B to C. You're going to have your total load times your length over 2. The total load, once again, is 68 pounds per foot. And this time we're going to multiply by 8 feet instead of 6, since B to C is going to be 8 feet. Once we plug that 8 in, divide it by 2, and that's going to give us a reaction from B to C of 272 pounds. Alright, finally we're down to the third step of this problem, which is going to be finding the reactions for the columns themselves. And once again, that's the same formula as the beam reaction. The only difference is, before we can insert the total load here, we have to add the beam self-weight, which was going to be 10 pounds per foot, to the reaction weight, which was 204 pounds. So once we do that, it's actually going to equate down here to 214 pounds per foot. And once we have that, we're good to insert that right into the formula. That's going to be 214 pounds per square foot, or pounds per foot, times 16, because we're looking at this section right here, over 2, and that's going to equate to 1,712 pounds. And that's going to be our A1. So next we're going to move down to A3, same formula, and we can use the same load that we calculated here, because it's just for this whole beam, this whole column, row of columns across. And once we do that one, only difference between this one and this one is going to be the 12 foot, because we're looking at this section now, and because that's going to be A3. That's actually going to equate to 1,284 pounds. And to find A2, well, A2 is equal to A1 plus A3. So literally, to only find A2, all we have to do is add the 1,712 pounds and the 1,284 pounds. And once we add those 2 together, that's going to give us 2,996 pounds, and that is going to be our A2. So what we just did is we just found each one of those grid points for this whole column, this whole row of columns for A. Now we're going to have to skip, I like to skip B personally and move to C, because you're going to need C and A to find B. So if we drop down to C, C is literally the same process we just did. So before we can put that live load right back in the equation, we have to take the 272 pounds, add it back to the self-weight. That's going to give us 282 pounds per foot. And same process, plug it back into the formula, 282 pounds per foot times 16. Once again, we're looking at this section from here, from 1 to 2. That's going to equate to 2,256 pounds. And jump down to C3, same thing, plug the same thing in again, except for the length, remember, it's going to be 12 feet this time instead of 16, because we're looking from 2 to 3. And once you equate that, that's going to be 1,692 pounds. And it's the same scenario as the A's. C2 equals C1 plus C3. So 2,256 pounds plus 1,692 pounds is going to give us our C2 value, which is 3,948 pounds. And B is almost similar to these, but since B is in the middle, it's having to support both of them. So we have to add the 204 pounds that we found from reaction AB and the 272 pounds that we found from reaction BC. And not only add those two, but also add the beam self-weight, because remember we have to include the self-weight of the beams themselves. And that's going to give us a total load for row B of 486 pounds per foot. And then once we have that, it's plug and chug, same thing as it was for A and C. Use the same formula, use the load we just calculated, which is 486 pounds per foot. Multiply that by 16, because we're looking at the 16 section right here. That's going to give us 3,888 pounds. And B3, same equation. Remember, you have to use 12 foot because you're looking at this section right here. And that's going to give us 2,916 pounds. And B2 equals B1 plus B3, just like the other ones. So when we add 3,888 and the 2,916 pounds, we're going to get a total of 6,804 pounds. Alright, and so finally we're down to literally just putting the answers up on the board. And we have all 9 of these grid points for each one of these reactions for each column. But before we can actually report the answer, as you can see from here, we actually have to take the reactions for each one of these columns and add in the column weight, which is a step a lot of people forget. You have to add that column weight of that 100 pounds. So basically that's what I did here. I went through each one of them on A1, A3, B1, B3, and C1, C3, and I added my 100 pounds to it. And the only variation to this is for A2, B2, and C2. You have to keep in mind that since those columns are actually in between those two, they're actually supporting both. So to do that, you're going to want to add, so we'll take B for example. From B1 to B2, remember we said it was 3,800 pounds. You're going to want to add the 3,800 pounds to the reaction we got from B2 to B3, which was 2,916 pounds. And once you add those two together, before you add the 100 pounds, you're going to get 6,804. And then remember, we have to add the column self-weight of 100 pounds. You get 6,904. And it's the same exact scenario with A2 and C2 as well. Just got to be sure to add both of the reactions, the initial reactions, and then be sure to add in your 100 pounds for the column self-weight. And once you do that, this is the answers you're going to have here, and that is going to represent the reactions for each 9 of the columns supporting that structure.